In this video, we will learn to solve equilibrium calculations with extremely small k value. That is, k is less than 10 to the power minus 4. Let us look at an example. Consider the dissociation of a duplex DNA sequence according to the following equation. 1 mole of duplex DNA dissociates to form 1 mole of the top strand and 1 mole of bottom strand. The equilibrium constant for this reaction K is equal to 1.0 times 10 to the negative 6. If we start the reaction with 1 milliliter of 2.0 millimolar DNA duplex, calculate the concentrations of all the species, that is duplex, top strand and bottom strand at equilibrium. First, let us set up the reaction table. We need to write the balanced chemical equation, the initial concentrations of all the reactants and products, the changes in these concentrations during the reaction, and the equilibrium concentrations of all the reactants and products. Let me first write down the balanced chemical equation. 1 mole of duplex dissociates to form 1 mole of the top strand and 1 mole of the bottom strand. We are starting the reaction with 2.0 millimolar DNA duplex and 0 millimolar top strand and 0 millimolar bottom strand. Since we only have reactants and no products in the reaction mixture at the beginning, the system will move towards products to reach equilibrium. Let us assume the concentration of the DNA duplex, that is reactants, decreases by x molar before reaching equilibrium. According to stoichiometry, for 1 mole of DNA duplex that dissociates, I get 1 mole of top strand and 1 mole of bottom strand. Therefore, if x molar DNA duplex dissociates, we will get x molar top strand and x molar bottom strand. At equilibrium, the concentration of DNA duplex is 2.0 minus x, the top strand is x, and the bottom strand is also x molar. Next, let us set up equilibrium constant expression K. For this reaction, equilibrium constant K is equal to the concentration of top strand times the concentration of the bottom strand divided by the concentration of DNA duplex at equilibrium. According to the reaction table, the concentration of top strand at equilibrium is x molar and the concentration of bottom strand at equilibrium is also x molar, and the concentration of duplex DNA is 2.0 minus x. This number should be equal to the equilibrium constant which is given, that is 1.0 times 10 to the negative 6. If we simplify this, we will get a quadratic equation which is very difficult to solve sometimes. What we are going to do now is use the value of equilibrium constant and our understanding of extent of the reaction to make some assumptions about x. These assumptions will drastically simplify these calculations. Let me first represent the reaction coordinate. On the left hand side, we have 0% products and 100% reactants. The Q value is 0. And on the right hand side, we have 100% products and 0% reactants. The Q value here is infinity. The K value for the given reaction is a very small number. So let me represent the K on the reaction coordinate. It will be closer to Q is equals to 0, which means when the reaction reaches equilibrium, the concentration of reactants is way greater than the concentration of products. We can say that the reaction strongly favors the reactants at equilibrium. If we start such a reaction with extremely small K value with only the reactants at the beginning, the reaction will move only slightly to its product side before reaching equilibrium. In other words, since the equilibrium mixture contains a very large amount of reactants compared to products, to reach the equilibrium point, only a small amount of initial reactant must be converted to products. So, our assumption is the following. The value of X, that is the change in concentration of reactants to reach equilibrium, is very small relative to the initial concentration of the reactants. That is, X is way smaller than 2.0, or 2.0 minus X is approximately equal to 2.0 molar. This assumption reduces the equilibrium constant expression to the following. K is equals to X times X divided by 2.0 is equal to 1.0 times 10 to the negative 6. As we can see, the assumption we made drastically simplified the equilibrium constant expression. If we solve for X, we get X squared is equals to 2.0 times 10 to the minus 6 and X is equals to 1.414 times 10 to the negative 3. The next step is to check if the assumption we made earlier is valid or not. This is a very important step. Our assumption is that X is small relative to 2.0 millimolar, which is the initial concentration of DNA duplex. And the value of X we calculated is 1.414 times 10 to the minus 3 millimolar. Let us see if this value is small relative to the initial concentration of DNA duplex, which is 2.0 millimolar. The way we do it is, we calculate what percentage of initial concentration is the value of X. That is, we calculate the value of X divided by the initial concentration times 100. If this percentage is lower than 5%, means our assumption is valid. If it is greater than 5%, which means that our assumption is not valid, and we need to go back and solve the quadratic equation to solve for X. For this problem, let us calculate this percentage. The value of X we calculated is 1.414 times 10 to the minus 3 divided by the initial concentration is 2.0 times 100. If we do the math, we get 0.07%, which is way less than 5%. Therefore, our assumption is justified. So, from the reaction table, the equilibrium concentrations of top and bottom strand of DNA is equal to X, that is 1.41 times 10 to the minus 3 millimolar. And the equilibrium concentration of duplex DNA is 2.0 minus X, that is 2.0 minus 1.41 times 10 to the minus 3 millimolar, which approximately is equal to 2.0 millimolar. At equilibrium, the duplex DNA is the major species present in the solution, while the top and bottom strands are the minor species present in the solution. In summary, the following are the steps involved when solving the equilibrium calculations. Step 1. Assume either the reaction goes to 100% reactants or 100% products. This is a limiting reagent type problem that we need to solve. Step 2. Set up the reaction table or ICE chart. Step 3. Solve for X, assuming X is very small relative to the initial concentration of the reactant. Step 4. Check the validity of the assumption by calculating X over the initial concentration of reactant times 100. This value should be lower than 5% for our assumption to be valid.